All right, I get to start all over. There we go. So here's a disclaimer. This is about rigging. You can see all the different types of configurations. Please use this information at your own risk. All right. Let's start out with the standard. Probably the one of the that needs to be addressed most often is you'll choke this material up. You don't know where to put it because you don't know the sling length, right? But what's left over is the leg. So if you choke it up and you have 4 feet left over, you're going to take that divided by 2 and move it that distance away from the center of gravity. And then you'll do the same thing the other leg, and then you have a 60 degrees right here, which is a nice angle. It doesn't want to slip towards the center. Slings don't want to slide towards the center of gravity when it's lifted. And it's not a, but it's very stable, and it doesn't have a high tension factor, right? So the tension factor being 4 divided by the height is how much more sling. So right here you've got, let's say it's 1,000 pounds, 500 pounds of vertical force on each side, right? Well, if you have to lift 500 pounds with a rope at an angle, you have to pull more than 500 pounds to get that vertical lift of 500. So the factor is what that is increased by. And you get that by one, you divide the diagonal by the height and then multiply it by that 500, give you the sling tension. Simpler than that, but anyway, so if you go here, it's real simple to locate it and to know what it is. And maybe you remember that it's 1.116 times for that 60 degrees. You can calculate it by going 4 squared minus 2 squared is equal to the height squared, which is that right there. Square root of 4 squared minus 2 squared. And that will give you the vertical. And then you do the multiply 500. You do 400, 4 divided by that, which gives you 1.1547. And then you multiply that times 500. That'll give you 577. Yeah, we go to, oh yeah, you can multiply to get this, just to get the sling tension factor right away. You just go 1 divided by sine of 60 times 500 right away, and it'll give you straight out doing it that way, but there's just algebra. That times 500, 707, so you get sling tension at 707. All right, then 30 degrees is real simple. It's just double, right? 500 vertical component on each side, and then it's 30 degrees. You get 1,000 pound tension on each leg. Here's an example, an illustration of it. If you just had a really steep, so your choker's just barely big enough to get to the shackle of the connection points on each side, and I've seen this happen. You try to lift it up. In this case, the very small, you have 0.34 feet, so basically it's only 4 inches. And then you start lifting that up, you'll actually get more because those things will probably start to stretch quite a bit before they bust. Because 3.34 and 7-foot diagonal your sling will give you 11,683 pounds of force, a sling tension. Easily rip apart your shackles, your slings, your connection points, and also asymmetrical loading. So it's not it's relative to the center of gravity, right? And typically you'd have like the 500 and 500, 500 with 60, and it'd be double like the other ones. This would be 866, and the other one was 500, but it's not. Should have just said 866. I forget what it was, but 707, 578, but it's not. So what you need to do is you need to find out how much the vertical component is at each location. So imagine if you put this beam on your shoulder and your shoulder's right here, you could balance it and keep it level with your arm extended way out here. your arm this way out there is not lifting a vertical component of too much, right? Compared to what's sitting on your shoulder. In fact, if your shoulder was right here, it almost would balance itself. You could just barely touch that and lift it up to keep it balanced. So it's a ratio. And the distance is exactly what the ratio of the distance, but the ratio of the distances is exactly the amount of weight that each one's going to carry. So the algebra looks like something like this. So X is, we're going to, I don't know why I call it X, it should be W plus W equals 1,000. So the weight of, let's call that a small w, not the total weight, small w. That's a small w. So the weight at this location, that's this unknown, plus the ratio of the distances of that weight. Right? So this is going to be the same weight, but it's a ratio of that weight, right? Here's the weight, and here's the ratio of the weight. What's sitting out here is both of those together is going to equal, when you add them together, going to equal 1,000 pounds. So if you do 1W plus 26W, you end up with 1.33W. Right? And then if you do the algebra there, you end up with W, which is the weight at this location, is equal to 750. And then 1,000 minus 750 over here would give you 250. You could do it opposite direction too. I don't know that I ever have. I think it would be interesting. Anyway, so we have 750, which is the weight, times. So now we're going to get the sling tension. We had the vertical component, and then to lift that with the sling angle of 60 degrees, that is, or you use a 60 degrees. 4 divided by the 3.46 times the vertical component of 750 will give you 867. And that's how that's done. And then over here, it's just 30 degrees with the 250 vertical component. I don't know why I end up with, I think it's because the 6.93 is, this rounds up. So then we have, so if you take this information here, we're looking for W, right? What is W? W is the weight, total weight, divided by the inverse of this ratio here. So it's 2 divided by 6. So divided by 2 divided by 6. Oh, yeah, and then it's 1. So you have to add the 1, right? 1W plus the ratio W. We end up with 1W, 1 plus the ratio here, D1 and D2, D1 and D2. And it's being moved over here. It's moved to the other side, but it's still on the bottom, so it's still D1 divided by D2. And then you have, so that's this portion, right, for W. And then you want the sling tension, the sling tension factor, right, which is the L1 divided by height H2. So L1 divided by H. So there's L1 and there's H. And then you just do a little bit of simplification and you'll get this formula. And you'll see that formula around. All right, so that's what I did here. And then, so I did it this way also, just with the formula to see if it works. And there you go. So that's why that works. And then you have a rigging configuration here where your slings are, let's say they're equally spaced, and then you're going to slide it. Let's say you need to get it lifted an angle like that, or whatever angle, right? You're going to take this and slide it over to calculate those weights. You just use that same formula. Except, oh, this is not the same formula. It is, you have different heights here now, right? So you have to plug in the 2 different heights with the 2 opposite sides, like we did over there. And anyways, there's the formula. So it looks like L1, stress factor for here is the distance 2 times the weight times the height 1, and then divide that by distance 1 divided by h1. What did I just do? Let me start over. d2, distance 2, times the weight, times the L1. d2 times the weight times L1 divided by d2 times h1, d2 times h1 plus d1 times h2. It's easier to do geometrically in my head than explain it with words, right? Of course. So, and then L2 is just the opposite. This one times the weight times the diagonal divided by, and then the divide by is exactly the same. It doesn't matter the order as long as you opposite times the height, opposite times the other height. That gets you the sling tension, and just to so you know that just leaning at this amount, the sling tension is almost getting close to 1,000 pounds on the leg, right? It's almost doubled, even though it doesn't look very unusual. So one of the things that will happen when you get a load that's up in the air and it gets hit something and it's leaning like this, right? But if it was coming down and it hit something here, well, the sling tension on this leg goes up really fast, especially with like it gets hit with the shock load too. So you got to be careful for that. That's why I always use a safety factor. Like a 5, safety factor of 5. So might be 3. I think it's 5 for personnel. Maybe. Do your own research. Here we go. It's just now here you can see that it's leaning like that, and it's increased by. It is actually more than the total weight on this leg is more than the total weight of the part, and on the other leg it's actually going less than the 500. Same formula. I just thought I'd illustrate. There's a counterbalance rigging beam. This is on a remote that goes back and forth to counterbalance. So when it's sitting at rest, this counterbalance is in the middle, sitting underneath. And as you start to lift the load, it will increase the lifting capacity by moving away. So like this situation, it's on the crane's just hanging there with this in the middle. And then you hook it up, and then as you start to lift, this starts to go uphill, and that's when you start moving it out till it levels out and sits off the ground, just barely going uphill, and then it'll eventually level out, lift up. So let's see, we have here we go. So this is just showing you this problem is the same geometry as the other, because what happens is the lifting capacity is more rotation or the lifting distance of mechanical advantages out here. So if you had the same formula X, I'm calling it X, I could have called it W, right? But and then you divide 1125 by that ratio, you end up with the vertical component of 959 at this location, so 960 pounds of vertical force needed here. And then you multiply 4 divided by 3.46 times that vertical component, you get 1109. And that's the tension here, the sling tension, 1110, right? And then the same thing over here, you have 1125 minus 960 is 165. And then the ratio of 12.13 divided by 3.46 gives you the sling tension of 579. But that's where it comes from. That's the geometry. All right. And an unusual case, this occurs if, let's say, you don't have enough headroom, some sort of a hoist that's attached to a floor, and then this is going up this has happened with stairs. You could put the rigging way up high, right? That makes sense, or the crane hook. But if you can't, there's nothing above it to attach it to. You crib it up off the floor as high as you can. Still have your hoist maybe right here and the hook. Let's say that's the point where you want to lift it from. So you're gaining a lot of headroom, but you're putting the sling, and maybe it looks counterintuitive, but the sling can definitely go uphill But what happens here is you just got to make sure that you use the same formula, 3.833 times the weight times the sling length divided by the 3.833 times this plus 2 times this h becomes negative. So you have to put in a negative 1.142. And then you do that for both sides. And then you'll see that the sling tension on this L2 is 819 pounds at that height. The higher you go, the more it gets, the more it goes up. And it goes up to the point where it's actually the same as what we just looked up here, the extreme case, right? Kind of like this. This one is, let's say that line was straight, or very, very, let's say right here. So if it was straight, it would be infinite, right? You could not have a connection point here and a connection point here and then lift it here and have it lift up without putting an infinite load on those 2 points, right? So right here, what happened is, just to illustrate that, to actually confirm that this is the case for the calculations, did a test and it came out correct over there, but it was similar to this. But to see if the limit was correct, okay, let's take it to the extreme. And that line was straight, it should be impossible to lift that, right, with those rigging like that. And so we have 3 times the weight, 1125 times 5, divided by the 3 times 4 plus 3 times negative 4, right? And it ends up being like this number divided by 0, which comes out to infinite. So let's say this was 3.99999. Let's go T. Let's copy this right here. Control C, do tools, calculator, Control V, and that's instead of negative 4, let's go 0.3.9999999, and then compute should be like 565 trillion, right? So it's approaching infinity, right? Anyways, that's how I check that. And then what I know about rigging, there's more, but this is kind of like one block of typical rigging scenarios. I think I did a video a while back on how to rig this up, like how to do it. It's the same thing as when I started. Put the first sling on there, and it dictates. You put it on there, choke it up. You just need to make sure that where you're going to connect to the 2 points is above the center of gravity, and the center of gravity may be not on the material itself. It may be out here like this in space. This line has to be above that to be stable, right? If you connected it here and here and it was below that, it would flip, it would tumble. So this length, in this case, the sling length that's left over is 4. You just swing that loop over until it intersects this line, and then from there to there is what you use to get your next sling height. If the sling was a little long, you would drop it down. Raise it up higher. If it was too short, you would have to bring it down closer to, to shorten it up, or use some sort of coupler or chain fall or something to make it adjustable, right? Don't usually need to make it adjustable if you know what you're doing. Like you could put 2 slings here together and make it accommodate, or double choke. And anyways, that's how it's done. And then this one intersects the vertical line of the center of gravity, perpendicular to this part if we were lifting it straight up. And then this one intersects both, right? It has to be exactly that length. So it's really kind of starting here, and then you're sliding this up and down here to adjust the length so that it matches that point. Do not use a regular shackle here. Shackles have usually 120 degree. You might see this one here. The shackle will have a maximum of 120 degrees. Here you need to use a lifting ring to connect these two, right? shackle to a lifting ring, a shackle to a lifting ring. Because if you use a shackle, they're not designed to be lifting up that steep of an angle more than 120 degrees out then. But unless maybe they make some that do. Right here, 136, right? It would be beyond the limit of 120 degrees. And let's see, pretty sure this one right here is 120 degrees. So typically you'll see the limit of 120 degrees. So the limit you to a 30 degrees on the horizontal, like a company policy or something. That's what I know about that, and it's a lot of information. I think the rigging classes is like 40 hours or 80 hours or more, so hope that helps in your career. Thanks for watching. Try to subscribe to make these easier for other people to find, because it's kind of difficult to find these videos because I'm not putting too much information in the titles and the engineering that goes behind YouTube. So if you're interested in this and you want more of these videos, let me know. I think every time I think I'm out of videos to do, I come up with something else. I can do these for the next 10 years, I'll bet. So thanks for watching. Please subscribe and share. Have a great day.